In this video, I will be discussing the structure of ceramics, taking a closer look at their unit cells and the arrangement of the atoms in each one of these and their properties. So let's go ahead and let's review some definitions. We already reviewed these definitions on the previous video that talked about the metal crystal structures, but let's review these once again before we discuss the ceramic crystal structures. So a crystal structure is a 3D periodic array of atoms. The crystal lattice is a representation of the arrangement of those atoms. A unit cell is the smallest volume of material that contains all unique features of the crystal structure. The coordination number is the number of nearest neighbors for a specific lattice point. And the lattice parameter is the cube length and can be expressed in terms of the atomic radius r. Lastly, the atomic packing factor is the fraction of unit cell occupied by atoms. So let's jump in and talk specifically about the ceramic structures. It's very important for ceramic structures to be stable because they are formed by cations and anions. The cations are usually smaller than the anions because as we remember from chemistry, the cations are the ones with the positive sign, which means a lack of electrons. Now the anions contains a negative sign, which means excess of electrons. So for a ceramic structure to be stable, the cation and anion have as many nearest neighbors of the other type as possible. They must have that. And the anions surrounding a cation are all in contact with that cation. So this one, the last one, is the most stable because all of them are in contact with the cation in the center. This one, the one in the middle, it's labeled as stability limit because these anions that are touching each other are repulsing each other. Now, in comparison with the third one, they are more spaced out. So there's a higher stability here. And the first one is very unstable because besides the fact that the anions are touching each other and are repulsing each other, none of them are touching the center of cation. Okay. Now, we already went over the definition of coordination number, but something very important for the ceramic crystal structures is the ratio of cations to anions, which must be determined to ensure neutrality. It also is very important because the ionic radius gives us the likely crystal structure. So professionals of the field have created this table which they have researched all the types of ceramic crystal structures, and they have created this table which is very useful for us because it tells us this stoichiometry of each crystal structure. So for example, if the ionic radius gives us a value in between 0 and 0.155, the coordination geometry is going to be linear. But if the radius ratio gives us a number between 0.155 and 0.225, we're gonna have a triangular geometry. If the radius ratio gives us a number between 0.225 and 0.414, we're gonna have a tetrahedral geometry. And if the radius ratio gives us a number in between 0.414 and 0.732, we're going to have an octahedral. Geometry. Lastly, if the radius ratio gives us a number between 0.732 and 1, we will have a cubic geometry. So let's go ahead and let's start looking more deeply into each type of ceramic crystal structure. One that's very known is the rock salt crystal structure, which is also called the NaCl crystal structure. For this one, the coordination number is 6, which, as we've seen in the previous slide, it is an octahedral geometry. So if we take a look here, we can see clearly the octahedral geometry right here. It is composed of interlocking FCC structures, and because the crystal structure is composed of two types of atom, the lattice parameter is much more complex than the lattice parameter of metals crystal structures. In the case of the rock salt, it is only 2 times the radius of the cation, which in this case is sodium, plus 2 times the radius of the anion, which is in this case is a chlorine. The total number of atoms inside of this crystal structure is 4. The next crystal structure is going to be cesium chloride, CaCl. The coordination number is 8, and if you look back to the table, it is a cubic geometry. It has interlocking simple cubic structures. The lattice parameter is 2 times the radius of the cation plus the radius of the anion over square root of 3. And it has a total of 1 atom. Now, you must be careful with this one, because even though it looks a lot like a BCC structure, it is not a BCC structure. A BCC structure is for metal crystal structures because it is formed of only one type of atoms. But in this case, the center atom is not the same as the corner atoms. So it is not BCC, it is cesium chloride. The next crystal structure is zinc blende. The zinc blende crystal structure has a coordination number of 4. It also has an FCC lattice, and the lattice parameter is 4 times the radius of the cation plus the radius of an anion over the square root of 3. It has a total of 4 atoms inside of the unit cell. It is highly covalent, and if all the atoms are the same, it is also called a diamond. So it is the structure of a diamond, but to be a diamond, it needs to be all the same atoms. And that is all for the crystal structures of ceramic materials. And that completes a review of the structure of the unit cell for ceramic material.